work. I'll put this over here. What's up? All right, so because R is a constant, no matter whether it's the initial condition or the final condition, you can say that PV over NT for this condition is the same as PV over NT for that condition. In other words, if the initial ideal constant is the same as the final ideal constant, which it has to be, then what must be true is that like P1 V1 over N1 T1 must equal P2 V2 over N2 T2. So that like little joke I made in the slide deck about you only need to know 3 laws, Avogadro's law, the ideal gas law, and the one who smelt it dealt it, which isn't a gas law, is a joke because you only need to know the 2 gas laws. The Avogadro's law, where 1 mole of a gas has a volume equal to 22.4 liters at STP, and the ideal gas law, PV equals nRT. Because when you consider that the ideal gas constant here is the same as this one, then the pressure times the volume divided by the number of moles and temperature here is equal to pressure times volume divided by number of moles and temperature there. A lot of times some things don't change. If this is a sealed container, the number of moles of gas does not change. So in this equation, if N1 and N2 are the same, then you get the equation P1 V1 over T1 is equal to P2 V2 over T2. That's a gas law called the combined gas law, which sometimes you would like memorize or have to know it as the combined gas law. You could also have a change, like if you just take this gas and compress it down to this volume just by squeezing it at a constant temperature, so it's the same number of moles and a constant temperature, then N1 and N2 are the same, T1 and T2 are the same, and you get P1 V1 is equal to P2 V2. And that's another gas law, which sometimes people memorize. You could also have a change where the volume doesn't change, number of moles doesn't change, and you look at the pressure and temperature relationship. So on each side of the equation, it's like P1 over T1 is equal to P2 over T2. And similarly, you could have a change where the pressure is constant, but the volume changes and the temperature changes. And then in that case, it's like V1 over V2 is equal to, or V1 over T1 is equal to V2 over T2. So in that form, which is really a solution of the ideal gas law, solve for an initial and a final condition where the number of moles doesn't change, you just get rid of or cover up the parts that you're not looking for, and you can end up with a final solution. Here's a really, there's 2 important things to know about using the ideal gas law. One of them is this. If you have an initial pressure of, let's say, 2.5 atmosphere, the volume is 3 liters, and the temperature is 20 degrees C, and you want to know how many moles of gas are in that sample. If you use the ideal gas law all by itself, PV equals nRT, to solve for the number of moles, N is equal to PV over RT, you can't stick any of those numbers into this equation because none of them are in the correct unit. Because the ideal gas constant, 8.31 joule per mole Kelvin, is in standard units in physics, atmosphere is not a standard unit of pressure. Pascal is. Liters is not a standard unit. Cubic meters is. And although degrees Celsius, you might say, well, that's a temperature in the metric system. Why can't we just use degrees Celsius? In this equation, this is an absolute temperature. It has to be in Kelvin. It cannot be in Celsius. Because think about this. What if this gas here had a temperature equal to 0? How many moles of gas would then be in there? An undefined number, or like 0? Like, what does that even mean? What if the temperature was like -5 Celsius? Well, that's positive, 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 -5. You'd have like a negative quantity of particles, which doesn't make any sense. So these temperatures must be absolute temperatures in Kelvin. That pressure, if you go 2.5 atmosphere, you know, 1 atmosphere is the same as, 1 atmosphere is the same as 1.01 times 10 to the fifth Pascal. The volume, I already showed you how to do this, but to get from liters to cubic meters, you got 10,000 liters in a cubic meter. So 3 liters, it's 10,000 liters is a cubic meter. The ideal gas constant is 8.31 joule per mole Kelvin. And then to get from temperatures in Celsius into Kelvin, you got to add 273. So if you have a temperature in Celsius and you add 273 to it, that gets you to a temperature in Kelvin. The dimensional analysis there isn't like a thing you should really deal. It isn't. This would still kind of have the unit degree Celsius, but you're taking a temperature in Celsius, adding 273, which makes the value in Kelvin. So I don't know. You got 2.5 times 1.01 times 10 to the fifth times 3 divided by 10,000 divided by 8.31 divided by 293. This is like 0.0339 mole. And then if you want to know the actual number of particles, you can use Avogadro's number to get you from like molar quantity into an actual quantity as number of particles itself. Mole day's coming up, I guess, huh? 16 days from now, on the 23rd. 23rd, like, because 6.02. If they're individual atoms, it's number of atoms. If they're molecules, It's a Friday. That's a remote day, which makes the party even better, I guess. Might not be a remote day for long. Well, that'll still be a remote day for us. The school board is trying to decide if we should be doing school differently. There, there's a sentiment to come back to be 5 days a week, but the remote option would also be available. Well, that's not a decision I make. That's not up to me. If you want to know my opinion, I'm not going to do it on camera. Well, see, the challenge is the best way for everyone to learn the most optimally is to have everyone here 5 days a week. But that's the most optimal way to spread disease and kill people. So, the best way to stop the spread of disease and not have people die is to all be fully remote. And that's not great either. But neither is hybrid. So, there's no obvious and simple answer, right? And that's a decision that has to be made by the school board. They are elected to make those decisions. The difficulty of the job I have to do changes dramatically when those different types of learning have to happen. But I'll do what I got to do, I guess. Okay, so there's that. Now, here's another thing I'll say. Here we had to convert from atoms into pascals, liters into cubic meters, Celsius into Kelvin. But what if you're considering a change in the gas? So this is an atmosphere liter degree Celsius. And let's say that as a result of like heating this gas up, we'll just make the temperature higher, like 40 degrees C. So, oh, and a thing, this is not double the temperature. We haven't doubled the temperature from 20 to 40 because the temperature only goes from 293 to 313. You know what I'm saying? So don't think that 40 is twice the temperature of 20. You've got to convert them into Kelvin to compare the two. So the temperature goes up and the volume goes up. So let's say the volume becomes, uh, 4.5 liters. Is the pressure the same as it was before? Is it higher? Is it lower? Like, how does that happen? The number of moles doesn't change. So this is like a sealed container. We haven't introduced gas or taken any gas out. In that case, if you're going to use this equation where it's like P1 V1 over N1 T1 is equal to P2 V2 over N2 T2, whatever doesn't change can go away in the equation. So if it's a sealed container, the number of moles is the same, the N's go away. And it's just P1 V1 over T1 is P2 V2 over T2. So long as the values are absolute values or absolute quantities, the units don't matter, meaning these pressures don't have to be in Pascal, because if they're the same unit, they'll end up canceling out anyway, along with the conversion factor. The volumes can be in any unit you want as well. The temperature is the only thing that has to be in Kelvin. So it turns out that I can use 3 liters and 4.5 liters so long as I'm comparing initial and final conditions. So now if P1 is what, or P2 is what I'm trying to solve for, you can solve the equation for P2. P2 is going to equal P1 V1 T2 over T1. You can take the initial pressure, which was 2.5 atmosphere, times the initial volume, 3 liters. They don't have to go into Pascal and cubic meters, but you'll get the same answer if you do. But the temperatures have to be in Kelvin. You can't leave the temperatures in Celsius. So what's that, 313 Kelvin divided by 293 Kelvin? And that'll get you the new pressure. You can see here that the temperature went up a little bit, but the volume went up dramatically. I can expect that the pressure won't go up proportionally to the volume, despite the fact that the temperature rose. The temperature didn't really rise by very much. 2.5 times 3 times 313 divided by 293, it's like 8.01. Hold on. I'm missing a V divided by V2. Can't believe I didn't put the V in it. 4.5 liters. So I was like, that's way too high. 8.1 divided by 4.5. Oh, don't give me a syntax error. 9.4 divided by 4.5. 1.78. That's good. 1.78 Pascal. So the pressure in that gas is lower than it was initially. We're going to study different types of expansion and the reasons why expansion and contraction happen and changes in volumes and gases and stuff. Another big idea here is that if there's a before condition and an after condition, you have to always consider that there is some energy here in this gas, and there's also energy in this gas. And that energy is either the left side of the equation or the right side of the equation, because this is really in the unit joule, and this is also in the unit joule. And it could be that the energy in the gas is constant from the initial to the final condition. But if you were to have a certain amount of energy here, present just in the particles, and then you like add heat, the amount of energy in this gas is however much this had initially, plus the heat you added, gets you the new amount of energy that happens to be in the final gas. Yeah. Oh, atmosphere, I meant. Yeah. Because, yeah, it's whatever that unit's going to be. Sorry. Just thought I have it. Yeah, like here, like you see liters cancels, Kelvin cancels, leaves you atmosphere. So whatever the unit is good. These can be in any. Like, these volumes could be in like gallons. We never use gallons, but it could be gallons and gallons. It doesn't make a difference because you really have like a proportion, like 3 liters over 4.5 liters. This ratio is the same whether you leave it in liters, convert it into cubic meters. It could have been in gallons. It could have been anything. You could say like, you know, it could be in an arbitrary unit, like the gas that fills a propane tank. You don't even know what volume it is, but if you were to take the gas or the gas in one propane tank and put it in 4 propane tanks, you could just be like 1 propane tank, 4 propane tanks. because the proportion of the volume is all that matters, not the absolute volume. Yeah, the temperature has to be in Kelvin. Because what if, like, you know, negative, it doesn't make any sense. You can never go wrong by putting temperatures into Kelvin. So another example is like in the equation to calculate change in length, like delta L is L naught alpha delta T. This can be in Celsius or Kelvin. Because if the temperature goes from like 20 degrees C to 40 degrees C, that's a delta T of 20 degrees C. This in Kelvin is 293 Kelvin, goes to 313 Kelvin. That's still a delta T of 20 Kelvin. So if in the equation you have a delta, it can be either Celsius or Kelvin because the change in temperature Celsius and the change in temperature Kelvin have the same value. If you're not sure what you should do, put them in Kelvin and you can't go wrong. But if you leave it in Celsius, you can be wrong all day long. So absolute temperatures in Kelvin must be, or absolute temperatures, not as a delta T, but as a T must be in Kelvin. Delta T's can be in Celsius or Kelvin. Like, that's straight up a thing. They'll just be like, on the AP test, they'll be like, here's the equation, PV equals nRT. And they'll just maybe just give you a PV and an N and a T. And you're just sticking the numbers in they gave you. And you get an answer. I can guarantee it's going to be one of the four options. Because they're going to be like looking for people who are like, they'll be like, you might not even know what PV equals nRT, what those symbols mean, but you can like look at the list of variables, find the equation, start plugging numbers in, get an answer, and it's going to be a choice. It's absolutely going to be a choice. The wrong answers aren't random values. They're the right answer, and the three things people screw up the most. And you can complete an AP test, feel like you got the whole thing right, because every problem you did, the answer was there. And then you get a 0 because no, you get a 1, but yeah, like you could get 0 of the multiple choice correct. Like you could actually be competent enough to find the variables on the equation sheet, correctly plug the numbers into equations, get answers for every problem, select the answer you get, and get every problem wrong. Because, uh, I mean, it's not as if it's just plug and chug calculation, but in the sense of PV equals nRT, maybe the pressure and the volume are both in standard units, but the temperature was given in Celsius. So there's only one thing you had to do, but you did that wrong. Sometimes it deals with discussions, like I don't know if it's like this on other AP exams. In physics, it happens. In chemistry, it happens, where there'll be like a scenario, and then there's students who have like responses, and your job is to determine which of the students was right, which one's wrong. Kind of like an assessment sort of deal. And it would not be uncommon in a problem with gases or with work and energy, PV problems with gases, to have somebody have a discussion about temperatures. Be like, well, the temperature went from positive to negative, so that means the volume becomes negative. Well, negative volume has no meaning in this world. Negative numbers of particles has no meaning. These values can't be, none of the values could be negative. Like in a lot of our equations, you could be like, well, if P is negative and V is negative, and it makes this side positive and this side's positive, and it all works out. There are no negative allowable values. It doesn't make any sense. It's just not how the world works. These are not vectors either, so they can't have a sign. It isn't like, oh yeah, well it's volume, but it's going to the left, so it's negative. That doesn't mean anything, Which way's the box going? Left. Oh, well, it's a negative volume then. Well, the one thing I will say, which we'll deal with temperature, is in a sample of gas, you have particles that are going left and particles that are going right. So you have individual particles with negative velocities and positive velocity. But temperature is actually a representation of kinetic energy. And kinetic energy is 1/2 mv squared. And the two important things about the equation for kinetic energy is that the kinetic energy varies with the square of the velocity. So doubling the velocity quadruples kinetic energy. That's an important idea with mechanics. But because velocity can have a sign, if you have a particle that's going in the positive direction, it has a positive kinetic energy. But if you have a particle going in the negative direction, it also has a positive kinetic energy, because when you square a positive number or square a negative number, you get a positive number. So kinetic energies are always absolute and always positive. So in a sample of gas, you statistically have as many particles going left as you have going right. You got as many going up as you have going down. Because otherwise, if the gas in this room all decided to all go that way all of a sudden, we'd get a vacuum up here. I wouldn't be able to breathe. Uh, there'd be a high pressure back there, and I'd be like forced against the board, and that doesn't happen. So what happens in a sample of a gas like the air in this room is you have as many particles traveling in each direction on a statistical basis, but the kinetic energy is only determined based upon, well, we say upon the velocity, but really it's upon the speed, square the speed. Yep, that's true. Yes, the probability is incredibly low, right? If you sample the pressure of the air or the density of the air in different parts of the room, it's got to be different places. But the time scales are very short because the particles are moving very quickly. I'll show you how to calculate like velocities of particles, but the air in this room, the particles are moving on the order of hundreds of miles per hour, but the mean path distance they travel is submicroscopic. Like the distances the atoms have to travel before they run into another is well smaller than the scale that you would be able to see. It isn't as if there's be so because of the vast quantity of particles, the high velocities, and the short distances they travel, the distribution of gas in this room is very consistent. If instead the gas in this room were represented by like only 3 soccer balls, the possibility of all three being at that end of the room is much higher, because there are so few particles with such huge distances between them that the probability of them clumping up is very high. There could be a moment in time with 3 soccer balls bouncing around this room completely elastically, and they could all combine and collide at the same time, like right here, all be in about the same space at the same time, leaving a void in the rest of the room. That's not impossible. So, statistical mechanics plays a very important role in thermodynamics. We'll deal with a little bit of that, but that's fun. That's usually in a field in thermodynamics, but it's a very important problem in chemistry. Like, I took 2 courses in physical chemistry in college. PChem. Oh, there's a sticker up here. Honk if you pass PChem, because it's quite difficult. It's very mathematical.